zero and liftoff of Space Shuttle Atlantis, reaching the crest of its historic achievements in space.
Astronauts must face a number of risks to their health and well-being. Among them is a problem that is shared by many who have never ventured into the hazardous realm of space, and that problem is bone loss.
Bone loss is a concern for NASA because when astronauts go into space flight, the body begins to adapt to the weightless environment, and one of those adaptations is that people start to lose bone. And the way I like to think of this is that the body understands what it needs to hold you up, and it builds your skeleton accordingly. And when you go into space flight and suddenly you're not walking around, you're not carrying the same mass, the body works to break that skeleton down to build you what would be a space normal skeleton, if you will. That would be fine if you were going to stay in space forever, but the astronauts want to come home, and we need to make sure that the skeleton remains as strong as possible during flight so that when folks come home to Earth, that they're not at increased risk of fractures or other problems.
As part of an ongoing effort to better understand the changes that take place in bone density during spaceflight, as well as how to counteract bone loss, NASA has partnered with researchers at Arizona State University on a study designed to develop a new technique for detecting bone loss. Ariel Anbar is senior author of the study.
The methods that exist right now are X-ray-based methods, and they're not particularly sensitive. By the time you detect that there's bone loss, the patient has already lost a significant amount of bone, and you already have a problem. So we wanted to see if there's better ways to do that, and we had the idea that measuring calcium isotopes in urine or blood would be an alternative way that could be more sensitive, and that's the research we set out to do.
But unlike conventional biomedical research, ASU's bone loss study had its origins in the field of earth science. Anbar, a geochemist, and his colleagues found a way to bridge the gap between two very different disciplines.
In the world of geochemistry, we have a whole bunch of tools and techniques and approaches to trying to study complex systems. Right? The Earth is a very complex system. Lots of stuff is going on. And we try to develop techniques that allow us to figure out what's going on with a relatively small number of measurements. And so we've developed ways of doing that over the decades. And we've thought for a long time that these methods ought to be useful in biomedicine as well.
The science behind the bone loss study is based on the chemical behavior of calcium isotopes. An isotope is one of two or more forms of an element that has a different atomic mass. In the human body, the abundances of these isotopes can function as indicators or biosignatures of changing bone density.
The basic idea behind the study is that when your bones are forming, your bones preferentially will take up the naturally occurring light isotopes of calcium from your blood, and that's what's actually forming your bone. So when your bones start breaking down, you have these light isotopes that are locked up in your bone, and if your bones start, dissolving, that light isotope signature comes back out into your blood, and you can measure it in your blood and urine.
The ASU researchers examined calcium isotopes in the urine of participants in a NASA bed rest study. The healthy test subject remained in bed for 30 days in order to simulate the effect of weightlessness on the body.
The results were very exciting. What we showed in this paper is that we can rapidly and quantitatively measure bone loss by just measuring calcium isotopes in urine samples. So what we showed is that after about a week of bed rest, subjects' calcium isotope composition changes consistent with bone loss. So this technique has a lot of value on a couple of different levels. First, the primary benefit that I see is that it has the ability to accelerate bone research in general because of its ability to rapidly detect the changes and quantify them. So instead of waiting 3, 6, 9 months to measure difference in bone density scans, we can now look and see if an osteoporosis drug, for example, is being effective, or if a countermeasure on the International Space Station is being effective on much more rapid timescales.
The potential benefits of the ASU study may extend far beyond the realm of astronauts. At the Mayo Clinic, Dr. Rafael Fonseca treats patients with multiple myeloma, a disease that affects the white blood cells and causes significant bone damage.
We're interested in the process of bone preservation and bone loss. The reality is that as we go on in life, there's a number of factors that can make an individual have loss in the density of their bones. It's important to remember that bones are living parts of our body. I often compare them to coral. They seem like they're just structures there with no life, but in fact, every day there's new bone being formed, there's bone being resorbed, there are cells that are in charge of the nutrition of the bone, and therefore it forms part of our health or our disease when the bone is affected. The consequences are very obvious. If someone has bone loss, that can lead to compression fractures, and in certain disease states, damage to the bone can lead to an actual fracture. And these are, of course, medical problems with grave consequences for individuals.
Dr. Fonseca is partnering with the ASU team on further bone loss research and is optimistic about the implications for patient care.
We still have a long road to go through in the process of learning about these markers and their utility in the clinic, but I think there's hope and there's sort of a shining light that tells me maybe we'll have that marker for predicting bone disease in patients where we really don't have it right now.
It is very nice to see that this research that sometimes seems just, even to us, maybe a little esoteric, right? Measuring isotopes in old rocks to figure out what life was like 2 billion years ago, that the same techniques could potentially be used in the very near future to improve people's lives. That's very rewarding.